And we are live. Okay, so without further ado, let's get to business. So this week's exercises, they were lagging a little behind in terms of what kind of questions we had, because we already started talking about the normal distribution, but I didn't have normal distribution related questions here. There were some in the Friday example session. Why I haven't yet posted the Friday example session model answers online is that I haven't yet translated all of them. I have translated most of them, and we talked about it already on the video, but I will put, there are many now there that discuss the normalized normal distribution and how to use the 0-1 distribution, normal distribution to answer questions about normal distributed variables. It's a very important topic, but we need that a lot during the last 2 weeks. So I opted to put more of those exercises in the last 2 weeks, and this week still covers the other topics that we've discussed this month. So the first one, why I wanted this question, the number one, is that we have a random variable and we talk about the median. Now, we've only talked about the expected value and the variance. And I've hinted at, when we talked about the moment generating functions, I hinted at that there is possibly higher momentums of random variables, ones that describe various topics like how far along the tail the distribution is. Tail heavy, I say. I haven't talked about it that much, but you know, the very rare events that occur, how rare are they exactly? That kind of depends. And then there is the asymmetry of the distribution. So if you look at the definition of the expected value, there's no way from the expected value and the variance alone to express the idea of is the expected value the average, if you will, such that it's very close to the one hand side of the distribution, and then there's a long tail of large values. For example, if you look at the incomes of people, the income of average income is high, but you may still have a great many poor people if you have a few very, very rich people who make a boatload of money, and you know, they skew the average, but then most people will still be earning not that much. So one way to assess this, which is a very crude and rudimentary way, but one way to assess this is to compare the median. And you've heard this term median income, median height, something like this. So in statistical sense, median means the value that is at the smack middle of the distribution in terms of the values or the actual occurrences of the elementary outcomes. So for instance, if you have a median in terms of a population, then half the population is below that and exactly half is above that. Of course, if the distribution is perfectly symmetric, then the median and the expected value are the same. But if they're not, then they're not. I have here two examples in this question, two examples of distributions that are not symmetric, and we calculate their medians. We know there's something about that relationship between the median and the expected value. So the first question was calculate, I'll have to, just a second. I'll share that. All right. So it drew some weird line there for me. So if we look at the median and the expected value, calculate the expected value and the median of this kind of a function with this density function, f of x equals 2x. So if we look at if we draw the curve of this density function, we notice that the curve of the density function looks like it looks something like this, right? From 0 to 1, and then it rises from 0 to 2. So we notice here that if we calculate the expected value, it's roughly 2/3 of the way. So it's 2/3 of the way there. That's roughly 0.6. I'm not going to draw a picture but it's halfway, more than halfway. And then if we calculate the median, then we calculate, how do we calculate it? Well, obviously we need to look at we need to look at this cumulative distribution function. And the cumulative distribution function, oh, sorry, there should be a capital X here. The cumulative distribution function at M should be 1/2. So we solve this for M. And how do we solve this? We calculate the integral from 0 to M over the density function 2x. And that should be equal to 1/2. And if we calculate this integral, well, that's 2x squared divided by 2. So that would be just x squared. And at the upper limit, that's m squared. And at the lower limit, that's 0. So m squared should be 1/2, which means that m is 1 over the square root of 2. So if you punch these two different, compare these two different numbers. Compare these two different numbers and we punch them into a calculator. I have no, so 2/3, that's 0.66. And 1 over the square root of 2 is 0.7. So the median is 0.7, and the expected value is somewhat below that, 0.66. So it means that if I draw, now I draw a picture which is just indicative of this. Okay, so we see here that this, and I'm going to just call this M, and we're going to call this mu. Sorry about my bad handwriting. So the capital M here means median, and mu means the expected value. So we have a situation where the median is higher than the expected value. And it is because, you know, this expected value is drawn this way because these are pretty far away from the median. These because the median is roughly there, right? You see, this is often when it happens. If you have this high peak and then a longer tail, then the average tends to be towards that tail from the median. That you can see from the income distribution of people, for instance. There are people who earn millions and so forth, but the average person meaning if you calculate the average, you get certain number. And I'm just throwing these from the top of my head. I don't know if they're correct at all, but let's say that the average income would be 4,000 euros per month, but the median income might be like 3,000. So whereas if you calculate the average, then you get a high number, but higher number than if you just take the one where half the people fall below that. I'm just throwing these numbers. I have no idea if they are accurate in Finland but just to give you an idea, that's roughly how they are. Look it up in the statistics, and here you should understand why this is so. So part of this educating here, I want to focus on this question very heavily because I want to educate you on this difference between these two measures, the median and the expected value. Okay, we have the exponential distribution. Not notoriously, there are far more heavy ones here. So if you take this, you do the same thing. We calculate the cumulative distribution function, integrate from 0 to m over the density function, 1/2. We get the integral of this is minus a to the minus mu x. Evaluated at 0, evaluated at 1. Evaluated at 0, that amounts to 1, minus 1, but you subtract it, so it actually 1 minus e to the, because this is minus and we evaluated at m. So that should be half. If we subtract 1 from both sides, we get minus, this is minus half, and then multiplied by minus 1, we get e to the minus m. Lambda minus m is 1/2, and we can, this is the natural logarithm of 1/2, which is in fact minus the logarithm of 2. And you take the negative, divide by minus lambda, you get the logarithm of 2 divided by lambda. But the expected value of this, is, we didn't calculate it here, but the expected value of the exponential distribution is in fact 1 over this lambda. So this is somewhat higher, lower, because logarithm of 2 is under 1, because the e is over 2. So this is lower than the expected value. Again, this is as a tail, so it's got a zero. It's a diminishing. The density function of this looks something like this. The density function looks something like this. So here it's at 1, and then it starts diminishing over there. So we have an expected value and the median somewhere in here. So the median is actually here, and the expected value is above the median. This happens with the narrow tail again. For grading this question, I gave here some rough guidelines. 1 point for each A and B. If there's a wrong answer, it's acceptable if it's because of some calculation error or something like this. I mean, solving this equation. But the idea must be somehow visible that you need the cumulative distribution function, and you have to solve it at that because it's given here. This is not a very hard question. All right. Let's go to number 2. So we have a continuous random variable with the density function f of x equals x over 12. And then we have to calculate the new random variable 2x minus 3 and calculate the density function and the sample space. Well, the sample space is obviously, we can calculate the edges at the, simply at here 1, it's minus 1, and at 5, it's 10 minus 3, that's 7. This is an increasing continuous function. So we can apply theorem. I'm not sure actually, this number 2.18 might be wrong. I have to change that. This was in a previous material called theorem 2.18, but I think this material, the numbering is different. So forget about that number, I'll change that. So we have this function h of x is 2x minus 3. That's the function that you would apply to x to get the y. And we calculate the inverse. So the inverse at y is, the inverse of that function is y plus 3 over 2. If you calculate this derivative of this inverse of h, it's 1/2. I mean, it's 1/2 y plus 3 over 2. And we get this theorem, which we can use to get the g of y. And it comes down at y plus 3 over 48. You can verify, integrate over this region, and you will find out that that's actually what happens. Notice here something. We calculate the expected values of x and y. Oh, sorry, there's a t there. It should be x. That should be x. I'll fix that too. So yeah, luckily I didn't publish them. That should be the integral of, and it's just x times f of x. So we get the expected value 3.44. The expected value here is the expected value of this. It's 3.889. We could just as well calculate the expected value by simply applying, this is a linear function here. It's a linear function. So we could apply this, it's 2 times the expected value of x minus 3. Well, we can verify it here. 2 times this would be 62 over 9 minus 3. That would be 63 minus 27. That would be 35. Yeah. sorry, 62 minus 27, that's 35 over 9, and it should be. So, you know, you don't have to calculate it this way. You can just apply directly the fact that the expected value of y is 2 times the expected value of x minus 3, because it's a linear. Why is there 24? Where is 24? You asked, why is there 20? Where? Oh, this one. Oh. It's f at this inverse. So if we divide this, this is the inverse is y plus 3 over 12, and we put that in place of x there. So that's y plus 3 over 2 divided by 12, and that comes down to 24 over there. Yeah. Sorry, I skipped that part. So you calculate f of x. So in place of x, you put this inverse of y, which is y plus 3 over 2. Yeah. So yeah, good question. I didn't know this to mention that, but that, yeah. Hey, please, anyone, if you ever feel confused about some part here, then just ask away, and the same guidelines for assessing this as before. Again, here, the expected value, you don't have to calculate it directly like this. For the y especially, you don't have to calculate it. You can calculate the expected value of y is 2 times the expected value of x minus 3, and that's correct too. I just did it this way, and you know, that's fine. Also, you can calculate it the hardest way is by taking this and multiplying that by y and calculating its integral. That is fine as well. You see, I'm using both these notations. I'm using this old school notation, which I've used, and in the first question, I used this bracket notation. I use both interchangeably, just to notice that you can use whichever notation you like for the integral. Either one is fine. All right. All right. Any questions about these first two questions now? The second one was really very simple. It was something that should have been in the previous weeks already, but I just thought, let's rehearse it a little bit more, because this is the sort of question that sometimes people have trouble with. Let's move on to 3. Sorry, my mouse is. So we have a product which lasts for t years without breaking, where t is a random variable. So we started using the product, and then after some years it breaks down. We don't know the distribution of t. We have no idea what the distribution is like. We have just experimentally determined that the expected value of this breakdown is 4.8 years. And it has a variance of 0.32 years. So we are asked to use the Chebyshev's inequality, or I like to call it T inequality because I'm really bad at pronouncing these. Using the T inequality to determine the lower bound for the probability that the product lasts for at least, because we have no idea of how this goes. We can only use the inequality as it is like this. So we have to figure out this for 3 years. So the probability that it's over 3 is obviously 1 minus the probability that the t is under 3. So we first find an upper bound. So to find a lower bound for this t greater than 3 years, lower bound meaning the probability is at most that, at least that, sorry. We had an upper bound for it to be less than this 3 years. So less than this 3 years, look, t is smaller than or equal to 3. So we have to get somehow x minus the mu here inside. So we subtract 4.8 from both sides. So we get t minus 4.8 is smaller than or equal to minus 1.8. And okay, so that's a negative value. Then we can take the absolute value from both sides. If we take the absolute value of this, this is negative, smaller than this is negative. We take the absolute value of both, then what happens to this comparison? Well, if we take the absolute value of two negative values which we compare, the smaller one will have a larger absolute value. So taking the absolute values, we arrive at this. That's t minus 4.8 absolute value. So whatever this is, it's not more than this. Why? Because this is the one, I'm going to just draw here a picture again. So if we have this distribution, we don't know anything about the shape of this anywhere, but you know, let's say there's the mu over there. So let's say that this is my distribution. We don't know anything about the shape, but let's say that this is my distribution and there's the expected value. And here's this part here is t minus 4.8. Sorry, that's minus 1.8, and that's 1.8. Sorry. So I have here this is a distribution of t minus 4.8 now. So I'm putting here a 0. I'm putting this at 0 because I'm now subtracting. The real t is shifted by taking this one that I've highlighted, this t minus 4.8 here. So I'm subtracting 4.8. So this is t minus 4.8's distribution, if you will. It's got expected value at 0 because t has expected value of 4.8. So I'm subtracting 4.8 from t. So we are calculating the probability that we end up in here, in the darkened region here. We have no idea how much probability mass, if you will, is there alone, but we do know from the Chebyshev inequality, and now I've highlighted, I've blackened both sides. We know that the T inequality gives us the probability here and here, these together. And this is definitely not smaller than this alone, right? This black region plus this black region. And that's the one where the absolute value is greater than 1.8. And now that's 1.8. That's my t. So I use the t inequality. I have 0.382 of the variance and divide that by 1.8 to the power of 2. Punch that into a calculator, if you will. You get 0.0988. And because this is the probability that we are in this outside region, then the probability that we are in this inside region, or in fact, what we are looking for is the probability. We are really looking for that probability over there. So we are putting 1 minus that. So now I'm going to just, I'll put these kind of I put these vertical lines. That's the region's probability that we calculated. That's 1 minus that. And notice that I don't include this tail. The actual probability is probably higher because it should also include this tail. All right. So this is the B part here. So what happens if we assume that the distribution is symmetric? Again, I'm drawing this. If we assume that it's symmetric, then we know that this part and this part have exactly the same probability mass because it's symmetric. So the probability that the t is smaller than the expected value, I mean, the probability that we deviate from the expected value in the negative side is the same as if we deviate from the probability if we deviate from the expected value to the positive side by the same amount t. Now, because of this, then we have that the probability that the t minus 4.8 smaller than or equal to minus 1.8, it's the same, it's actually half of this whole probability. Look here, we took in the first part, we took this step. We know that whatever this probability is, it's that other half of those two, again, I'll show this, of those two blackened regions here. We don't know their proportions. We only know that one of them, you know, this is the combined regions. So this is the left-hand side region. So the left-hand side region cannot be bigger than the two combined. But in this case, in the second case, we know that the left-hand side region is in fact exactly half of this. So we know that we can replace this by half of that. So we get the 0.988 at half. So this upper bound for t smaller than or equal to 2 is half of the previous assessment. We get that at 0.494, and we get that the probability is then 0.9506. So think about it this way. The first assessment for breaking within 3 years, or making it at least 3 years, was 90%. So the breakage probability was 10%. But in this case, in the symmetric case, the probability for breakage is just 5%. So it's half. We get a lot better assessment of that. So here the grading should focus on the proper use of the T inequality. 1 point should come pretty easily if it's somehow cited, but the second point would require at least some level of understanding that this in this B question, the probability should be higher. So think about the first one. We have no idea about how much probability there is in the left-hand side tail and the right-hand side tail. In this B part, we have the same amount of probability in the right-hand side and the left-hand side tail. So, but just as a review question before we move on, what does your intuition say? If this is symmetric, and what's the which situation has the higher probability that it will in fact last for more, let's say it will last for 10 years. If it's symmetric, what happens to the probability that it lasts for 10 years? Can you think about it? Well, if it's symmetric, what's the minimum lifetime of this? It's 0. So it's a good question. Almost, well, it's actually exactly 0, because if you think about it, the expected value is 4.8. The minimum value obviously is 0. So the maximum lifespan of this device cannot be more than 9.6 years. Because it's symmetric, right? If these probabilities are symmetric, then anything over 9.6 must have a probability of 0. If it's not symmetric, then it could be a very heavy tail of very long lifespans. So you see, it's not always immediately intuitively clear that if we get a better estimate, then we have a longer lasting product, at least in the extreme cases. Not going to go into detail here, but just a good review question. And it's almost 0 was a very good answer here. It's almost 0, pretty much 0, exactly 0. All right, here was question 4. This is some rudimentary algebra or dealing with summations, infinite sums, the series. So we generate the moment, we calculate the moment generating function for x. And the crucial part here is to understand the moment generating function is the expected value of e to the tx. So we just multiply the function with e to the tx and calculate the sum. So we get this sum here, e to the tx divided by 2x, and then sum x ranges from 1 to infinity. So we can take here, it's e to the t divided by 2 to the power of x, and that's the infinite sum. So let's denote this e to the t over 2 by z, and let's for now assume that z is smaller than 1. If z is not smaller than 1, if z is greater than 1, then what happens? For t's value greater than this, the logarithm of 2. What happens is that the sum becomes infinite, right? So we have to assume this. If we assume that this e to the t over 2 is smaller than, well, its absolute value is smaller than 1, we can calculate the sum, and then it's just, well, it's because the sum ranges from 1, then it's z over 1 minus z, and you get e to the t over 2 minus e to the t. So, yeah, if someone has calculated the sum and gotten something like this and not used any assumptions there and just denoted it like this, don't subtract any points from that. Technically, you should do that. The thing you should verify is that the moment generating function at least exists at t equals 0, but even that, don't penalize anyone if they didn't do that. Okay, don't. It's not. This is also a learning opportunity. So those who have done it, good for them. If they've done it, then you can overlook any other errors more. You know, you can overlook more of the other errors. It's very good observation, but it's not necessary. You can give the point if they calculated this to some extent or understood that you can somehow do this summation and get this. Another thing is that if they arrive at this sum and then they do the differentiation of this sum directly to get the answers to the B question, then that's fine as well. So don't worry about that. So the thing is that in any case, we should be able to calculate this m at 0. And in fact, most of these times when the moment generating function is of some importance, then the only thing we really need is that it's defined at 0 and at some point next to 0 as well. That's the crucial thing about this moment generating function. It needs to be defined at some interval that contains 0. But for your purposes, if it's defined at 0, then let's be content with that. Okay? Needs to be continuous at 0. But if it's continuous at 0, then there's no problem here. Or it's actually differentiable. It needs to be differentiable at 0. Well, this obviously is, and this works. And we can use that to determine the expected value and variance. Remember, the expected value is the derivative of the moment generating function at 0. So we put that at value 0, put that and find the derivative of that. That's 2 times e to the t over, I mean, if you look at this, if you do the, I didn't bother to do it in great detail, but you can take the product of the, think of this as a product and whatever you want, or you can use software. This is the derivative. You calculate the second derivative of that, you get something like this. And then subtract from the second derivative at 0, subtract. So this is in fact the expected value of x squared, and this is the square of the expected value of x. You subtract those, you get 6 minus 4, and you get 2. So this is a variance and expected value of 2 both. This is for the discrete exponential distribution here. All right. So if the definition of the moment generating function is somehow correctly invoked, then you can give 1 point, and the second point if you need to calculate, if you understand the need to calculate the derivatives. Also, if this was done very well, this looking at the limits, and also then you can overlook if there are more serious errors here. Just make sure that there are two really important, there are 3 important things, and 2 of them need to be correct or roughly correct. The most important thing is understanding the definition of the moment generating function, that it's this expected value, and you need to do this. So roughly, if this is roughly all right, this here, then 1 point. If in addition this is done correctly, that's the second point. If it's not done, then look at this, and if this is done roughly correctly, I mean, if there's minor errors in how the derivative is calculated, then don't subtract points from that. But otherwise, you know, just 1 point for B and 1 for A. All right. Any other questions for this, number 4? All right. Let's carry on. Number 5, a random walker walks on a plane with integer coordinates. We start at the origin and take 1 step every second. Doesn't really matter which the time interval here. Step is taken randomly, either towards east, west, north, or south. And the random variable d is defined as the distance from the origin after 2 steps. Determine the sample space density function, expected value, and variance of d. Now, I had a question this morning. Well, it actually came in the weekend, but I only read it this morning. What metric should d follow? Any metric is fine. I was thinking about the Euclidean metric, so that's the square of the distance, you know, x squared plus y squared, and then take the square root of that. You know, the distance from origin, Euclidean distance from origin. So if someone used another distance metric, then it's definitely admissible. Harder to check the answers because I didn't calculate it. There are various metrics that you could use. Of course, you could use the trivial metric, right? So it's 0 or 1. It's 1 if it's a different point, and 0 if it's the same point. But those are not, you know, not really the idea here. I was hoping, but sorry, 1 step, 2 steps away. If someone used the idea that it's 1 step or 2 steps away, you know, did they go? Well, it can't be 1 step away, because if you go 2 steps, then you either go back or you go further. So, but let's look at this. Let's first derive a random vector with coordinates after 2 steps. So we have these possible coordinates. We can get to -2, 0, -1, -1, -1, 1, 0, -2, 0, 0, 0, 2, 1, -1, 1, 1, and 2, 0, right? So it's, you know, 2 to the left, 1 down, 1 up, 2 down, then 1 up, 1 down, 1 left, 1 right, 1 right, 1 left, 1 down, 1 up. So the probabilities here, we calculate. There's only 1 case where this happens, that's 2 left. There are 2 cases where this happens, left and up, left and down, or down and left. 2 cases similarly for this. by symmetry for this and this also 2 cases. There's only one case for this, this 0 minus 2 and 0 minus 2 as well, because you get 2 steps in one direction. So all these 4 cases have 1 over 16, 4 cases have 2 over 16, and then this origin has 4 over 16. Sorry. And if we take then this density, then it's x squared plus y squared. So we have really only 3 different outcomes. It's 0, 0, and then 2 in the same direction, and then it's so back where we started, 2 steps in any one direction, or 1 step in both up and down directions, and there are 4 cases of this. So we get these outcomes, and the probability of getting back to the origin, that's the 0. So that's 1 in 4. The probability of getting that, that's 2, 4, 6, 8. So that's 1 in 2. And then 1 in 4 again of getting 2 steps away. So these are the probabilities. However you arrive at this situation or this conclusion is fine. I did this by enumerating all the possibilities. If you come up with some weird closed form way of expressing these probabilities, that's definitely fine. Or if you somehow come up with this, these are the distances. Now look here, the Euclidean distance, 1 up, 1 left, for example, that's that would be square root of 2. I mean, 1 squared plus 1 squared, that's 2, and the square root of that, and that's you know, 2 steps in one direction, that's 2 squared, and the square root of that is 2. So that's just the normal distance from the origin. And you get the expected value is simply, well, it's 0 times 1 over 4, square root of 2 times 1 over 2, and then 2 times, that's the 2 times 1 over 4. So that's 1 over 2. So we get square root of 2 plus 1 over 2. And this is our mu. We can calculate this, its square, and then we can calculate the expected value of the square of the distance. And if we calculate the expected value of the square of the distance, that's 2. And then we can calculate the variance, that's 5 minus 2 times the square root of 2 over 4. So this requires you to do it by hand. I don't think there's a reasonable assumption to be made where you can calculate this in some kind of closed form formula or come up with a function that is in a reasonable form. There's so few points here. Notice that there is a level of symmetry here that's destroyed by this. I mean, sorry, because of the symmetry, there are only 3 different value outcomes for this distance and so forth. It should be a little bit heavy on algebra. Evaluate this according to this idea that if you have somehow figured out that you need to look at these base cases and look at these cases of how far you get and then so forth, then evaluate these from the possible combinations. Then even if there's error made, keep points for that. If this is completely correct, you can already give 2 points for that. I mean, it's not that big a deal. In B, you should understand, this is a Bernoulli experiment again. I see there's a missing parenthesis there. So there are 5 random walkers. Well, it's a probability that at least 2 of them are back to where they started after 2 steps. Well, we just calculated the distributions for the 2 steps, and we're only actually interested in whether they make it to the origin. And then whether they make it back to the origin, it's the 0 idea, and it has 1 over 4 probability, and all the rest is, it lands somewhere else. So we get this K, is a binomial distributed variable. We have 5 walkers, each has 1/4 probability. And we calculate the probability that this k is greater than or equal to 2. So that's 1 minus the probability that it's smaller than or equal to 1. So that's 1 minus this case where no one ends up in the origin, minus then this case where exactly 1 ends up in the origin, and get 0.367 roughly. Here, the grading idea is that you recognize the fact that this is a binomial distribution from and the event probability comes from a part Walker's probability of ending up in the origin. If there's an error made in part A, but then whereby you get a wrong probability for this ending up in the origin, but this is calculated with that probability, but it's calculated correctly, then by all means give a point. If it's recognized as remember that the binomial distribution is a sum of Bernoulli experiments. So if you recognize the Bernoulli experiment as this occurrence here, then you should get a point here. And then the binomial formula may be different because you may have the wrong probability, but then as long as it's calculated correctly with respect to that probability, then you should give a point there. All right. Any questions for this? Okay, there are no further questions for this 5. Let's go to the last question. These questions were for the Poisson distribution. A healthy human has 6,000 white blood cells in 1 cubic millimeter of blood. We use the Poisson distribution to find the approximate probability that a healthy individual has at most 2 white blood cells in 0.01 cubic millimeter of blood. So this 0.01 cubic millimeters of blood is definitely less than 1 drop of blood. Blood has a very high surface tension. So if you drop it if you take fresh blood and take 1 drop, it tends to generate a very large drop, which is definitely has a diameter high enough so that it's not going to be, it's going to be more than the definitely more than 0.01 cubic millimeters, probably more than 1 cubic millimeter even. So this is something you take under a microscope, a very high level of magnitude, magnification, and look at it to identify the white blood cells. So we approximate this. 1 cubic millimeter has 6,000, and 1,000 of a cubic millimeter has 6. This is we assume that this is Poisson distributed, and so this here we speak in a volume. Most of the examples talked about time or space, distance, but this is volume. So we take a volume. I mentioned this volume already as an example. So we take lambda, the parameter, to be 6, and we approximate this with a Poisson distribution. X has a Poisson distribution of parameter 6. If we calculate this x smaller than or equal to 2, then we take the cumulative distribution function. Remember that the Poisson distribution's density function was lambda to the power of k over k factorial times e to the minus lambda. So here lambda being 6, we get e to the minus 6 times, and then the first one is 6 to the 0 over 6 factorial, which is then 1. It's always 1, plus 6 to the 1 over 1 factorial, that's 6, and 6 to the 2 over 2 factorial, that's 18. And that times e to the minus 6, we get 0.062. So if we take this blood samples and we take a small stain of it on a glass and we look at it at the microscope, we should see with probability 95 plus probability, we should see more than 2 white blood cells there, if the person is healthy. So this, I mean, this is, if you only see 1 white blood cell, or alternatively, if you see hundreds of them, probably in this is small enough. I'm not sure, I don't know the volume of white blood cells. Probably there cannot be hundreds of them, but definitely there may be tens of them. But if you see much more or much less, then it's, maybe there's something going on here. I don't know. In any case, this is a very common assumption, is a Poisson assumption when it comes to sampling something. It's this sample some waste management outcomes. You know, you have the sewage plant is processing water, and there shouldn't be more than a certain number of certain bacteria, for instance, in the outpouring water, and you take a sample, which then from that sample you look at the number of certain bacteria, and if it's lower than the threshold, then it's fine. If it's higher, then something's going on in that plant that it's not supposed to be. It's not filtering the water properly or something like this. Right. Any questions for 6A? Well, okay. A phone service is called 10 times per hour. We assume the calls adhere to Poisson distribution. A person working at the service takes 10-minute break from their work. What is the probability that there is at least 1 missed call during the coffee break? Well, 10 calls per hour means 10 per 60 minutes. So divide that by 6, that's 5/3 calls per 10 minutes. So that's 10/6, which is 5/3. 5/3 calls per minute. So we have a Poisson distribution with parameter 5/3. And it's easy because the probability that there is none is e to the minus 5/3. So at least one missed call is 1 minus e to the minus 5/3. So that amounts to 81%. So 10 times per hour, it's pretty sure that someone will try to call you during a 10-minute coffee break. Right. Sorry. Here, the grading for correctly identifying, meaning that you are correctly identifying the parameter here. This is 6 and this is 5/3. If one of them is correct or both of them are correct, then 1 point for that. So it's the idea of recognizing a parameter. And the second point, if this calculations, at least one of them is calculated correctly, then you get another point, right? Any question? So 6p, you got x is 5/3, but 5/3 is what it is distributed. I don't understand. You asked that you made a mistake, so I get any point for that. You got that x is distributed as Poisson 5/3, but exist if you got that correctly, you should get point. But look, if there is a calculation error here, minor calculation error in okay, let me rephrase that. You should get a second point if these are almost correct, if the calculations are almost correct. So simple miscalculation. I don't know what kind of miscalculation you made, but I would suggest that if it's a simple miscalculation, then I wouldn't give I wouldn't subtract points. But if it's a serious one that kind of shows that there is a excessive sloppiness, for instance, if you calculate simply the probability that it's exactly equal to 0, or if you calculate the probability that it's exactly equal to 1, then that might be cause for not giving points, unless of course you have if 6A is completely correct, for instance, or if 6B is completely correct, you should get 2 points. So minor calculation error should not be 1, but if none of the calculations are correct, then maybe it's just worth 1 point. I'm not sure. We'll have to see. I'll make this a little bit more accurate, this grading scheme. Any other questions here? Okay. Okay, so it seems like we made it through in less than an hour. If there are no further questions from any of you, I'd be willing to end our session here. I'm going to stop recording now. So if there are any offline questions you want to make after the recording stops, then you are free to do so.